Hello, Interspeech. My name is Juchang Li. I'm from National Taiwan University and Academia Sinica. This work is under supervision of Yu Chao and Xuantian Lin. I'm glad to introduce you our work, Seril, Noise-Adapted Speech Enhancement using Regularization-Based Incremental Learning. Here is the outline. I'll briefly talk about the background motivation in the introduction and then introduce our methodology, showing the setting and promising results in the experiment and give you the summarization in conclusion. The objective of speech enhancement is to transform low-quality speech signals into enhanced quality speech signals. In many speech-related applications such as automatic speech recognition and speech emotion recognition, SE is used as a preprocessor to remove noise components from speech signals. In many portable or assistive hearing devices such as mobile phone, hearing aids, and cochlear implants, SE is crucial for increasing speech intelligibility and quality in noise environments. Numerous noise adaptation techniques have been proposed to fine-tune deep learning models in speech enhancement for mismatched noise environments. The source domain means the noisy environment which the SE model has seen. The target one means there is some unseen noise that causes mismatch problems. In our paper, we assume we can derive a few pairs of data for adaptation. Note that most SE applications are applied to embedded devices. The nature of embedded devices doesn't allow solving the issue with additional storage of all pre-trained models or earlier training data. Adaptation to a new environment may lead to catastrophic forgetting of the previously learned environments, especially with few target data. The catastrophic forgetting issue degrades the performance of SE in real-world embedded devices, which often revisit previous noise environments. As you can see on the right side, the noisy speech which is polluted in the source domain cannot be enhanced well by the model fine-tuning in the target domain. In this paper, we propose a regularization-based incremental learning SE strategy, complementing existing noise adaptation strategy without using additional storage. With a regularization constraint, the parameters are updated to the new noise environment while retaining the knowledge of the previous noise environments. It allows the model to slow down the catastrophic forgetting effect and keeps comparable performance in the target domain. Considering the losses in the previous and new acoustic environments, LO and LNU respectively, the total loss can be formulated as the summation of the loss that derive in different environments. Because the training data of the previous environment is not usually accessible online, we cannot calculate LO term. Instead, we can assume that the loss of the previous environment can be revealed from the learned SE model with the parameters denoted by theta. We approximate LO by using the second-order Taylor expansion at theta equals theta star. Note that LO at theta star is a constant. We assume that SE model has reached to a local minimum, so that the elements in the gradient vector of LO at theta star are generally small enough to be ignored. Therefore, we can take the approximation of LO as a quadratic form. And then, we ignore the cross terms in the Hessian matrix at theta star to improve computational efficiency. Finally, we can obtain the regularization term. F theta I is the diagonal element of the Hessian matrix at theta star. The intuitive interpretation of F theta I is the local curvature, which indicates the sensitivity that affects the performance of the previous acoustic environment. Although F theta is equipped with rationality to avoid catastrophic forgetting, the commonly used curvature-based methods of deriving F theta rely on point estimation, which only capture local curvature information around theta star. In contrast, the path optimization-based method considers the information over the optimization path on the loss surface. In particular, the importance score is determined by accumulating over the entire training trajectory. The change in loss L over the time interval from TS to TE can be approximated by using the first-order Taylor approximation. Therefore, The change in the total loss can be represented as the summation of individual loss delta LTI associated with each parameter. From the references definition of importance scores, each score is divided by the change of parameters for normalization. Finally, we combine the advantages of curvature-based and path optimization-based approaches by interpolating the two strategies. In our experiments, we choose the scale invariant speech distortion ratio in the spectrum as our objective function. We use one-directional LSTM for real-time inference. For a training set, 2,000 utterances were randomly selected from the VCB corpus. Each utterance was contaminated with 13 types of noise from the NOISEX92 database at 6 SNR levels ranging from -3 dB to 12 dB with a step of 3 dB. This training set is termed T0. To prepare adaptation sets, we randomly select another 300 utterances from the VCB corpus. These 300 utterances were contaminated with other 4 types of noise from the non-speech database: cough, door moving, footsteps, and clap. We compare the serial and the direct fine-tuning approach in terms of the adaptation capability and the degree of catastrophic forgetting. The pre-trained and noisy are also our comparison. We use the training set T0 to train one baseline model, turn M0. Then, based on the 4 adaptation sets, we sequentially adapted the model from M0 to M1 using T1, M1 to M2 using T2, M2 to M3 using T3, and M3 to M4 using T4. M0 to M4 were then tested on 5 testing sets. The SDR scores of 5 models are tested on the 5 testing set are shown in the above figure, as you can see the difference between serial and naive fine-tuning. It is obvious to see the distortion caused by the catastrophic forgetting effect. The above table shows the SDR, PSQ, STOI, and extended STOI scores of the final model M4 learned using the fine-tuning method and the serial on the 5 testing sets. All testing environments except for original, which is under a metric training testing condition for the baseline model. It is worth noting that compared with the direct fine-tuning approach, the serial requires only a small amount of additional computational cost and storage to set the constraints when performing a model adaptation. However, serial can produce performance comparable to the direct fine-tuning approach in each new environment while overcoming the catastrophic forgetting problems in old environments. When deploying a speech enhancement system in real-world applications, it is common to encounter a new noisy environment and revisit to previous noisy environments. Also, the direct fine-tuning approach can effectively adapt SE models to the new environments. The adapted SE model may suffer from the catastrophic forgetting problem. The proposed serial model not only yields comparable performance to the direct fine-tuning approach, but also effectively overcomes the catastrophic forgetting problem. To the best of our knowledge, this paper is the first work that incorporates incremental learning into speech enhancement. And our experimental results confirm the effectiveness of the proposed serial system for model adaptation and avoiding catastrophic forgetting.